Okay, so off we go. So yeah, Chapter 4. Believe it or not, we're going to cover all three sections of Chapter 4 today. There are a lot of analogies between optimization in multivariable calculus and optimization in single variable calculus. So that makes a lot of this kind of not that new. It's sort of an extension of things you already know. And also it's very mechanical. It's very algorithmic. It's very, I don't want to quite say plug and chug, right? But there's a process and you just follow the process and it's fine, right? So, okay, so first let's talk about Taylor polynomials. Y'all will recall Taylor polynomials such as this thing right here, right? Kth degree Taylor polynomial for a single variable function, certain regularity requirement, of course. No, we're not going to think too much about that sort of stuff. Now, why would we care about such a thing? And the reason why is because this is what you might call the simplest function that mimics some, whatever function f is that we're interested in mimicking. So it's a really nice way to take a function and have it behave in a morally equivalent way while still, in fact, being a much simpler function. So in particular, this means that it has the same value as f at the point A. It has the same derivative as f at the point A. Same second derivative, third derivative, fourth derivative, etc., all the way up to the same kth derivative as f at the point A. And so thus the what we call degree k. Okay. All right, so what's the multivariable version of this? It's the same basic idea. We're looking for a function that has, among other things, the same value as f at some base point that we're interested in understanding f. So at the point A. Now I'm going to say it has to have the same derivative, but wait a minute, there's a bunch of different derivatives, a bunch of different partial derivatives, right? So again, if it's mimicking f, it would have to have all the same partials, not just a single derivative. And then et cetera, and then all the way up to the kth order. And of course, there's a bazillion different mixed partials at higher orders. Okay, so I need the Taylor polynomial to agree with f in all of these senses to be able to claim that it's mimicking f. All right, so how do you do that? What's the formula? And it turns out that the general formula is actually, it's a lot, right? It's notation heavy and it's weird. But it's still pretty doable to write down for k equals 2. So you'll notice we're going to look here at the second degree Taylor polynomial for a multivariable function. And you'll notice a lot of familiar things. Starts off with f of a, no surprise. Second term, you kind of might even expect this. It's just the derivative times x minus a, just like in single variable. It's just that now the derivative's not just a scalar anymore, right? And where things get a little weird is this second order term. So, this is actually pretty strange. I'll say unexpected. Notice there's a matrix vector product, right? And then that gets dotted with x minus a. So strange construction, but a couple things I'll point out. First of all, that is a known construction. That's a quadratic form. Y'all may remember quadratic forms from Math219. And it turns out there's cool things that we can say about quadratic forms. Especially when the matrix in question is symmetric. And notice the matrix in question here, this thing's called the Hessian matrix. That matrix is indeed symmetric, right? Notice if you flip over the diagonal, you're just talking about different orders of mixed partials. And as previously discussed, for sufficiently nice functions, as we're going to focus on, those are always the same. So this is a quadratic form with a symmetric matrix, and more to say about that later. Okay, that's 4.1. Right, it's very quick. It's just a couple of things to be observed, and a lot of the rest of the stuff that's in 4.1 is review of old Taylor polynomial ideas that y'all have already seen before. Okay, I forgot to erase all of my here. Let me fix this real quick. Gosh. Sorry, I don't want to have to erase all of my junk. Okay, here we go. So, how to do what we call optimization. How do you find maxes and mins of multivariable functions? So I'm going to start by reminding you how single variable optimization works. Y'all have seen me do this a million times where I show you a point of view on single variable stuff because that is what generalizes nicely to a multivariable context. So here we go again. So if you are looking at a multivariable function, a single variable function, there is a collection of conditions you can write down with a nice punchline that the function is at that point in the process of increasing one way or the other, depending on how you're moving in the x-axis. And therefore, that the point in question is not a maximizer. Right? So, for example, this point right there, you look at this point in the domain. Let's just go ahead and infer from the picture as intended. That's clearly in the interior. It's not an endpoint. Kind of looks like the function's differentiable at that point, and the derivative is non-zero. So I claim that in one direction or another, the function's increasing at this point. And you might say to yourself, well, yeah, but as I go to the right, it's decreasing. Well, yeah, it's true. But as you go to the left, the function's increasing. Right? So this couldn't possibly be where the maximizer is. The function's in the process of getting bigger as you move to the left. Obviously not the maximizer. Okay, so here's the good news. This actually eliminates the great majority of points in the domain. None of those points could possibly be the maximizer that we're looking for. Now, okay, so what about these points that are left over? And I guess I'd better do about like that. Oh, and I can hit this button here. There we go. So what about these leftover points? Well, such as that point right there. That's an endpoint. That's not in the interior. That doesn't satisfy my condition. I can't apply my elimination process here. That might be the maximizer, simply because I can't eliminate it. Right? This little green strategy that I have here eliminates most of the points, but it does not eliminate that one. Ditto, that point, can't eliminate it. It doesn't satisfy the second condition. The function's not differentiable there. I can't even talk about the derivative. How can I conclude that the function is definitely increasing in some direction or definitely decreasing in some direction? I just don't know that because I don't know anything about how it's changing because the function's not differentiable. Right? Likewise, here the derivative is 0. I don't know what's going on there. Likewise, here the derivative is 0. I don't know what to say about that. And another endpoint. So there are points that I cannot eliminate. We call those critical points. The whole point to critical points is that we don't know what's going on at those points. So it's a common misunderstanding. A lot of people think critical point is just fancy talk for maximum, and it's not. Critical point is a point where we have no earthly clue what is happening at that point based on this sort of an analysis. Okay. How are we doing? Familiar? Okay. All right, so good news. Almost exactly the same ideas apply in a multivariable setting. And let's see here. Let me try to get this all on screen. There we go. So again, there is a set of conditions I can write down that allows me to conclude that that couldn't possibly be a maximizer. And so, for example, if you take this point right here, now notice I've drawn a graph over here of a function of two variables. Why am I drawing a graph? Well, I just want to be able to see, visualize what's going on. But at this point, and let's go ahead and infer from what's vaguely suggested by how I drew this. Yeah, it looks like as I move toward the middle of my domain, it looks like I'd be going uphill on this graph. It looks like the function's increasing, right? So presumably, the gradient not being 0, that means that, in fact, yeah, the function is literally increasing as I move kind of, if you will, sort of toward the middle. So that can't possibly be a maximizer. And again, this applies to most of the points in the domain. I'm not going to fill in the whole thing. It would take me too long. But most of the points in the domain, these three conditions apply. And all we're left then with is the points where one or the other of those conditions fails, such as this point where it's kind of flat and therefore the gradient 0, this point where it's got a sort of a pokey thing there on the top, so it looks like it's not differentiable, this point where it's kind of flat, this point where it's kind of flat, and then of course there's the boundary, right, which are points that are not in the interior. So other than those points, vast majority of points we eliminate. And the points we cannot eliminate, we, again, just like we did before, we call them critical points. This does not mean that they are maxima. Very likely they're not maxima. Maybe they are. Who knows? The whole point about this is that we don't know what's happening there. Therefore, we can't eliminate them as possible maxes. So now, what are they? What are the different versions of critical points? What might they be? Well, you'll notice that there are some points that really are maxima, local maxes, such as that one right there. That's a possibility. There's also local mins. You can imagine what that would look like. There are saddle points, we call them. You'll notice that it's sort of concave down, sort of coming out of the page, but then it's sort of concave up like that. And they call it a saddle point because at the time that they started thinking about this idea, the closest thing to that was a saddle. And I propose that if this were a new concept nowadays, they'd be called Pringle points. Because that's what they look like, right? Okay. So, saddle points is the term. There are more than this as possible. I want this. There we go. Possible classifications, and one that I think is fun, worth looking at, is this thing called a monkey saddle, and that's a real term. I did not make it up, and it's based on this little picture right here. And you imagine if a monkey were riding a horse, right? Hilarious. He'd need a sort of a down slope for each of his legs, and he'd also need a spot for his tail to go. So his tail wouldn't get squished, right? So notice this shape here, right? This shape is weird. It's not like a regular saddle, right? There's kind of 3 upward directions instead of 2, and kind of 3 downward sloping directions instead of 2. That's not a thing in single variable at all. Right? There's a kind of a better picture of a surface right here, less funny but more clear, and in case you're curious what that looks like. Just for fun, I also like this one here. This is like an insect saddle, right? There's a bunch of different down slopes, a bunch of different up slopes. That's nevertheless a perfectly reasonable surface and a possible way to classify a critical point. All right, so back to it. Okay, let's see here. There we go. Let's see an example of this in action. The algebra on this is really pretty quick. Don't forget to check all 3 conditions, though. Remember, it's not about the answer. It's about the reasoning, right? And it's going to be graded on the basis of, how complete and legitimate is your reasoning. And so you have to look for all 3 different kinds of critical points, even if there are none to be found by, whichever criterion you're looking at. You still have to check, and you have to show that you've checked that. So conveniently, a lot of these are easy. You look at this function right here; it's defined everywhere. The domain is all of R2. Every point in R2 is in the interior of R2. There's no boundary, right? So no boundary critical points. No differentiability critical points. It's a polynomial. It's differentiable everywhere. So that's a dead end as well. But you have to write it down. So make sure to do that. Easy money. I can't comment as to how many points, but it's easy to write down. Just go ahead and get those points, whatever they are. And then, okay, we have to take the gradient and set it equal to 0. Notice how analogous that is to single variable, where you take the derivative and set it equal to 0. This is kind of the same thing, right? So we take that gradient, set it equal to 0. That tells us our possible values of x. This tells us our possible values of y. And altogether, we get these critical points. Everybody good? Okay. Now, that's pretty algorithmic, right? The only other thing I need to tell you all about this is that the algebra does get a little weird sometimes. Single variable algebra, not so bad. It has its moments, though. I mean, it can be hard to do single variable algebra. Multivariable algebra, nonlinear systems, in other words, such as something like this, it's actually pretty hard to solve in general. So you sometimes have to consider cases. And I wish it weren't so, but sadly it is. So for example, how would you solve this system right here? The temptation would be to look at this and conclude that x is equal to y. A lot of high schools will kind of let that slide as, well, you know, you cancel the squares or something like that, right? And of course, it just doesn't work. It's just wrong. It is absolutely not fair to conclude from x squared equals y squared that x must equal to y. No, it doesn't. It could totally be negative y. These two possible cases are just as valid as each other. You can't just, I think I'm going to ignore that second one because it's weird, right? You just can't do that. So you have to consider each case separately. And so we'll start off by considering x equals y and see what follows from that. But then we're also going to have to look at what happens if x is negative y. Each one of these cases will give different critical points, and they are all real, valid critical points. And again, keep in mind as well, it's not about whether you find the right one. Like if the actual maximizer that you were looking for, if it happened to be that one, and you found it because you did this case, well, yeah, but if you forgot this case, the fact that you found the right point isn't at all what the grading is based on. We're looking at the reasoning, and if you miss a significant part of the analysis, then you missed a significant part of the analysis. Okay, so make sure to do them both. The algebra on this is very straightforward. If x is equal to y, you can plug that into there, which then becomes that, and that tells you your y values. Right? And then, of course, once you know your y values, then you can plug back into there to see what your corresponding x values are, and therefore the critical points. Okay, sure, fine, right, but what about if x is negative y? A whole new case, and you've got to do the whole analysis again. Notice plugging in to here gives you a very different, well, let's just say different, right, equation for y. Different answers, different values for y. And then likewise, these y values, you plug into there, and you get different critical points. Well, at least one of them is different. Coincidentally, one of them happens to be the same, that whatever. How we doing? All right, so please do take stuff like that seriously. Stuff like this really matters. Okay. All right, so there is a second derivative test for optimization. The single variable second derivative test is based on looking at the second order term, which you quickly persuade yourself is entirely dependent on the value of that second derivative, and thus the single variable second derivative test. You just have to look at the value of the second derivative. Right? Positive means minimum, negative means maximum. Okay. Well, in the multivariable case, that's our second order term. That's what I need to know. Is it always positive? Is it always negative? Is it not always either? Right? And so the quadratic form, again, we've already made that observation, and so we're interested in finding when is it positive definite, when is it negative definite, etc. And the fact that this is a symmetric matrix, again, does end up being really useful. Y'all will remember that symmetric matrices are diagonalizable, old fact from linear algebra, and diagonalizable matrices means you know certain things about the eigenvalues and blah, 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 a bunch of linear algebra stuff. Y'all don't need to go through that stuff, but you're welcome to, and this is kind of hitting the highlights. If you want to, walk your way through, feel free. But here's the punchline, and this is what you do have to know. And it's a little kind of flow chart of possibilities. Notice quite a bit more complicated than the single variable version. Right? Single variable version was real simple. Look at the second derivative. Positive, negative, end of story, pretty much. Well, first of all, let me recognize we're only even going to talk about this in the case of a function of two variables. It gets weirder with three or more. It's doable, and it's in the book, but we're only going to, in this course, focus on two variables. And here's how it breaks down. The first thing you have to do is look at the determinant of that Hessian matrix, sometimes called the Hessian determinant. So look at that, and you got to see whether that value is positive, negative, or zero, and then act accordingly. The positive case is the one that's kind of most familiar. The positive case, if that determinant is positive, then you kind of get what you might want to call like a familiar second derivative test. Look at the x second partial. Positive means min, negative means max. Just like in single variable. Right? So that's, like I say, kind of familiar, but that only applies if the determinant is positive. Right? If the determinant is negative, you get a totally different story. If the determinant's negative, it is a saddle point. What kind of saddle? Who knows? But it's a saddle point of some sort. Okay. Lastly, determinant, of course, could be zero. If that happens, then importantly, very importantly, the test fails. It does not mean that it is a maximum. It doesn't mean that it isn't a maximum. It means we don't know. It means the test did not tell us anything, and we lose. Okay, so also a possibility. All right. Example. Let's try to squeeze all this on. Here we go. So example, we've already found for this function, we found the critical points, and they were these 2 points right here. We just kind of left that as it was at the time. So let's think through now, how would we follow the above procedure for these 2 points? Well, one at a time. Let's start with that point. We can compute our Hessian determinant. This function, you can compute the various second partials, compute the determinant. You get this. Plugging in this point gives us a negative Hessian determinant. Negative means saddle point, and we're done with that critical point. Very pluggy chuggy. Everybody good? All right. right, let's look at the second one. Let's see here. We will look at 1, 0. Okay, 1, 0. Well, again, now we don't have to reproduce the calculation, but we still have this formula for the Hessian determinant. And 1, 0, again, you plug that in. It is positive Hessian determinant. Positive means I've got more work to do. Positive means I've got to decide about that second partial with respect to x. So what is fxx? Well, okay, well, fxx is this entry right there, and that entry is positive at this point. Again, keep in mind, this point, x is 1, y is 0. So that fxx is positive, and positive means local min. And we are done with that one. Everybody good? Okay. All right. Okay, so moving along. There's some really interesting things to be said. Call this just a quick hand wave towards some sort of mathematical formality. If you want to find what they call a global extremum, so the actual absolute maximum value of a function, it turns out there are some cases where, in fact, there is no such thing. And in order to avoid going on a hunt for something that doesn't exist, right? Always bad. You don't want to hunt for something that doesn't exist. It's nice to have this theorem down here, which basically has the punchline. Under certain conditions, there is a global max, and therefore it's reasonable to look for it. Now, how does this theorem work? Well, long discussion. We don't have time for this. But roughly speaking, there's in some sense really only 3 things that can go wrong. Now, again, I'm not going to talk about how to prove that. That's not what this class is. But you can see if you have kind of an open end, it's possible the function just keeps getting bigger and bigger. Or if it's unbounded, the function could just be getting bigger and bigger. Or if it's allowed to have discontinuities, then even in the middle, it could just keep getting bigger and bigger. Right? There's various different ways in which there could simply not be any sort of a maximum. So roughly speaking, what this theorem does with these 3 conditions, we're just eliminating those different possible ways that a maximum could fail to exist. And with those eliminated, there must actually be one. I just thought that was worth waving my hands at that. So we are going to have to understand how to check the boundary, right? Remember that there's this possibility the absolute maximum might be on the boundary. I'm going to show you 2 different ways to do it. One is I don't particularly endorse, but there are some circumstances where this can work, I suppose. But I'm going to show you a much better method in just a couple minutes. But you could take a real simple point of view on this, that if I'm, for example, interested in this function defined on the entire solid disk, and if I want to understand that function, though, on its boundary, and in particular on this part of the boundary, well, notice on that part of the boundary, I can just write y as a function of x. I can plug that in for where y is. And that means that as long as I'm only looking at this top part of the boundary curve, I can view my function as being effectively pretty much just a single variable function. Right? And so you can do single variable optimization on this function here. Now, the algebra does not work out particularly nicely there. You can see it's not so great. You can further see that I'm also going to have to entertain the underside, where there's a different formula for y, which therefore gives you a different formula for the function that you have to do single variable calculus to. So you have to do the whole thing kind of all over again, and that's, it's a little tedious. So most of the time, this is not a good strategy. And let me point out as well, this was assuming I could even solve for y. And the only reason I could solve for y is because this happened to be a really familiar geometric shape. And very often, you just won't get that lucky, and you just flat cannot do this. All right. Okay, so here's the much better method. This is called Lagrange multipliers. It's a very clever idea, and it's a part of a general idea called constrained optimization. So the idea of constrained optimization is I have some function I want to make as big as possible, thus the term optimization, right? But with the understanding that I can't just plug in whatever values I want. There's a constraint that I can only plug in just certain values that satisfy some requirement. So here's an example of a constrained optimization problem. Right here, we want to find a point on a given curve that's closest to the origin. So there is a function I want to optimize. The optimization aspect of this function is I want to make distance to the origin as small as possible. Now you'll notice this is not distance. This is distance squared. This is a real clever little hack, by the way. I encourage everybody to do this. If you think about it, the point that makes distance as small as possible also makes distance squared as small as possible. And it's a lot easier to write down distance squared than it is distance, because who wants to deal with square roots? Right? So that's no good. Okay, so there's the function we want to optimize. This is what we call the objective function. There is, however, another aspect of this problem. This is the constrained side of this problem. I have a constraint. Namely, I'm only allowed to look at these points. That's it. Any point that doesn't satisfy that equation, inadmissible, not interested. Right? I only allow points that satisfy that constraint. So how does that factor in? And, well, there's a real clever move on this, and that is to always write your constraint as a level set. Then look at the function whose level set gives you the constraint. We call that the constraint function. And if you set it up this way, if you view your constraint as being a level set of a particular function called the constraint function, then this Lagrange multipliers method is going to turn out to be extremely convenient, very powerful, very easy to use, and much better than the alternative we saw. So I, of course, have to show you what that is. Okay, how we doing so far, though? Everybody see how we're setting this up? Okay. Let me give you a couple of quick examples of objective function and constraint function. So here's a reasonable question. Engineers will be able to relate to this. Perhaps you might have a limited amount of materials. Right? There's only so much materials that you have. So the area, the materials you have to work with is fixed. That's your constraint function. If you're trying to find the biggest box, biggest in terms of volume, that blah, 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 you can't just say, I think I'll make it the size of this building. Right? Now, you don't have that much materials. That's not admissible. Right? So with the given constraint, now you have a non-obvious problem, how to make the box as big as possible. Okay. What is it that we're trying to make as big as possible? Well, volume. That's your objective function. So this phrasing here, this question, find the biggest box with a given area, that is a constrained optimization problem. All right, here's one from a sort of a business point of view. Let's suppose you are going to start a small business and you have a limited budget. You can't just say, I think I'll invest $10 billion on materials and labor, etc. No, you can't. You don't have that kind of money. Right? So limited budget is your constraint, and subject to that constraint, given that you only have X amount of dollars, how should you allocate those dollars? Labor, tools, materials, right? How much should you spend on what in order to make your productivity as much as possible? So that means productivity is your objective function. All right? That make sense? All right. So why is this business about level sets so convenient? There's a lovely little argument here. I'm not going to go through all the gory details, but it turns out this is actually not that different from single variable optimization in the sense that there is a collection of conditions I can write down that has the feature that any point that satisfies those conditions, the function is increasing and therefore could not possibly be a maximizer. And so, for example, as I have the picture drawn, this point right here, I'm calling A, that point could not possibly be a maximizer. Now let me walk you through why this works. What is it about this picture that allows me to instantly eliminate this as possibly being the maximum? Well, I mean, my two functions are differentiable, so I can use derivatives, gradients to talk about how the functions are changing or not changing, and that's all legitimate. And, I mean, it says right here that my constraint gradient is non-zero. We know something about gradients. Gradients are always perpendicular to level sets. That's why we wanted to set up the constraint level set. So I know that my constraint gradient is pointing perpendicular to the surface. And then what does this tell me? This right here then tells me that the gradient of f is not pointing in that same direction. The gradient of f has to be pointing off of the perpendicular. And if it's pointing off of the perpendicular, then it has a shadow. And in the direction of that shadow, make a geometric appeal. This is an acute angle. Right? And so therefore this dot product is positive, and that means the function is increasing, and that can't be a maximizer. Does that make sense to everybody? Okay. All right. So again, good news. This works most of the time. Most of the points in the domain will satisfy all of these conditions. And so it's only the ones where one of these conditions fails that we have to worry about. And so again, we call these critical points. Again, critical point means we have no idea what's happening at that point. Doesn't mean it's a max, doesn't mean it's a min. It means we don't know. Might be, can't eliminate it. I don't know. And here are the three things that you have to check. So now again, very important to go through all of these. It's weird to me, but it seems like a lot of students just like to gloss over these first two and get right to number 3, right? And I think the reason for this is that the actual maximizer, most of the time, it comes from condition 3, but not always. You can't take that to the bank. And so as reasoning, and keep in mind, it's about the reasoning, it's not about the answer, right? As far as reasoning goes, condition 3 by itself, completely insufficient. You didn't check for this possibility. You didn't check for this possibility. That reasoning would be invalid. So please do make sure to check all 3 conditions. Good news, these tend to be easy to check. They're going to be worth a little bit, point or two. It's easy money. Don't leave the easy money on the table, right? Make sure to get those points. Right? So take a look, make sure that the functions are differentiable. Take a look and make sure that the gradient of the constraint function is never 0. And then you can get down to the more sort of challenging question about this right here. Okay, let's see an example of this in action. By the way, we are kind of done with all the ideas. I have 3 examples remaining, you'll notice. We will get through as much of this as we can. So whatever we don't get done with among these three examples, I have a recording from last year at some point that I'll send y'all, where I'll talk through all these examples in great detail. You can see how all these examples work. But anyway, let's get through as much as we can. Here is our optimization problem. We want the highest point. That means we want to maximize height. We want to maximize z. So z is our objective function. Is that cool? Okay. Our constraint is we've got to be on this given surface. This surface is a level set, and conveniently, side note, it won't always be this convenient, but it's already written very conveniently as a level set. And so that means that our constraint function, the function whose level set is our constraint, is that function right there. And by the way, some people have a superstition that they want this constant on the right side to be 0. Some people like to subtract the 4 over to the other side, and then the constraint function will have a -4 in there. It doesn't matter. Suit yourself. It's harmless, but it's also completely unnecessary. Okay, so let's proceed with our process. Our first step, check for differentiability. No problem. These functions are polynomials. They're differentiable everywhere. I just earned a point on my exam paper, right? So again, I just got to eyeball it. Usually it's perfectly obvious. Yeah, differentiable, boom. Write it down. Point. Don't leave it on the table. Secondly, I've got to look at my constraint gradient, and I've got to worry about the possibility that it might be 0. Side note, just terminology. For reasons that we can't talk about in this course, this is called a degeneracy. For really good reasons, not appropriate for Math219. So just FYI, I'll typically call this the differentiability condition. This is the degeneracy condition. This is the Lagrange condition that, where a lot of the work happens. Okay, so checking for degeneracy. We take our constraint function, we compute the gradient, and now we have to ask, where is this gradient, constraint gradient, equal to 0? Well, linear algebra tells me that. Wanting it to be 0 is a familiar old Math218 question, right? So how do you, it's a system of equations, and you could row reduce or whatever you like. I personally think it's easier to make singularity arguments. This matrix, the determinant's not 0. I think this is a non-singular matrix. That means there's a unique solution. And 0 is obviously a solution. Therefore, it is the only solution. So it saves you a row reduction. I think it's kind of nice. Okay, now, a lot of people think that means it's a critical point. It is not. Keep in mind these conditions. These are conditions that we have to check among points that we are interested in as possible maximizers, namely points that are actually on our constraint set, right? So if a point's not on our constraint set in the first place, we don't need to eliminate it. It was never on the table in the first place, right? So don't forget, in cases like this, if you find a point that satisfies the degeneracy condition, it doesn't matter unless it's actually on your set. And the origin does not satisfy that equation, so this is not a critical point because it's not even allowed in the first place. That makes sense to everybody? All right. So now we're going to write down the Lagrange condition. Right, you take the gradients that we computed above. Here's the objective gradient. There's the constraint gradient. This says one is a multiple of the other. Particularly, the objective gradient is a multiple of the constraint gradient. And you can solve that system, and there's details that I'm not going to have time to talk about because we're out of time. But those details are in the recording I'm going to send y'all. The last thing I want to point out is, again, this only matters if you're talking about a point that satisfies your constraint. So, in fact, you need to find points that satisfy all four of these equations, because only if all four are satisfied is it an actual critical point. And everything else that follows is algebra, trickery. So watch those recordings I'm going to send y'all, and we're done. See y'all later. Have a good one.